The detection of 3I Atlas on July 1, 2025 by the ATLAS Asteroid Terrestrial Impact Last Alert System Survey Telescope in Chile represents a paradigm shift in observational astronomy, underscoring the capabilities and implications of modern, automated near-Earth object, NEO. The Atlas system, comprising multiple telescopes across the globe, is engineered for high-cadence all-sky scanning, primarily to identify potentially hazardous objects, PHOs, on collision courses with Earth. Its operational protocol involves capturing 4 images of the same sky field per night, with intervals of approximately 15 to 30 minutes. Sophisticated software then performs differential image analysis, subtracting a static master sky template to identify moving or transient sources. The initial flag for the object later designated 3I Atlas was automated. The system's pipeline, processing terabytes of image data nightly, identified a point source with a signal-to-noise ratio of 8.5 at coordinates right ascension 10 hours 45 meters 32.1 seconds, declination minus 25 30 feet 45 inches J 2000.0. Its measured proper motion was 15 arcseconds per hour, a rate too high for a typical main belt asteroid and indicative of a much closer or intrinsically faster moving body. The automated classification algorithm initially assigned it a 70% probability of being a known NEO, but a subsequent cross-match with the Minor Planet Center's MPC database of known objects returned no matches, triggering an internal alert level of new discovery, requiring verification. Dr. Marta Silva, the duty astronomer that night, was responsible for vetting these automated alerts. Her workflow involved a multi-step process. First, confirming the detection was not a cosmic ray hit or a charge-coupled device, CCD, defect by checking its point spread function, which was consistent with a stellar source. Second, she accessed near-simultaneous imaging data from the complementary Atlas unit in South Africa. The object's presence in both datasets, separated by approximately 7,000 kilometers baseline, confirmed its celestial nature and ruled out satellite or other anthropogenic origins. Third, she performed a blink comparison, rapidly alternating between the 4 images from the Chilean telescope. The steady, linear motion of the point source was unambiguous. The critical step was the submission of these 4 precise astrometric positions, right ascension, declination, and UTC timestamp, to the MPC. The MPC's automated orbit determination software, which fits preliminary orbits using the Gauss method, initially struggled to converge on a stable elliptical solution. The residuals, the differences between the observed and calculated positions, were unacceptably high for a standard Keplerian orbit. It was at this juncture that Dr. Silva manually intervened, forcing the software to compute a hyperbolic solution. The result was an orbital eccentricity, E, preliminary value of 1.18 plus 0.05. This was the first concrete, quantifiable indicator that 3I Atlas was not gravitationally bound to the Sun. The formal designation as the third interstellar object, 3I, followed from the MPC within 24 hours, once the orbit was sufficiently refined. Orbital calculation. The 72 hours of astonishment. The confirmation of 3I ATLAS's hyperbolic orbit was a global endeavor in precision, astrometry, and celestial mechanics. The initial MPC alert mobilized a pre-established network of follow-up observatories, including the Very Large Telescope, VLT, in Chile, the Keck Observatory in Hawaii, and the Southern African Large Telescope, SALT. The objective was to acquire high-precision astrometry over a sufficiently long arc to minimize the uncertainties in the orbital elements, particularly the eccentricity and the hyperbolic excess velocity, V infinity. The methodology relies on the fundamental principles of orbit determination. Given at least 3 precise observations of an object's position in the sky, one can calculate its 6 orbital elements: semi-major axis, A; eccentricity, E; inclination, I; longitude of the ascending node, omega; argument of perihelion, omega; and time of perihelion passage, T. For a hyperbolic trajectory, the semi-major axis, A, is negative, and the defining parameter becomes the eccentricity, which must be E greater than 1. The process is iterative and complex. The initial preliminary orbit from the Gauss method provides a first guess. This is then refined using a method of differential correction, often a weighted least squares fit, which adjusts the orbital elements to minimize the sum of the squares of the residuals, OC, observed minus calculated. For 3IATLAS, the high velocity and increasing heliocentric distance meant that even small timing errors in observations translated into significant positional uncertainties. To account for this, observers used ultra-precise GPS synchronized timestamps, accurate to within microseconds. The most computationally intensive aspect was modeling non-gravitational forces. For active comets, outgassing can produce jet forces that subtly alter the orbit, a phenomenon famously observed with 1I Aoumuamua. Teams at the Jet Propulsion Laboratory, JPL, and the Institute of Applied Astronomy in Russia ran independent N-body simulations. These simulations integrated the equations of motion for 3I Atlas under the gravitational influence of the Sun. All 8 planets, the Moon, Ceres, Pallas, and Vesta, using numerical integration techniques like the Everhart-Radau integrator. They also included a non-gravitational force parameter, A1, A2, A3, to model any radial, transverse, and normal outgassing accelerations. After 72 hours of continuous observation, the combined dataset from over 50 observatories yielded a definitive orbit. The JPL Horizon System published the final key parameters. Eccentricity, E, equals 1.32 plus or minus 0.01, and a hyperbolic excess velocity V infinity equals 58.4 plus or minus 0.3 kilometers per second. The moment of validation came when Dr. Kenji Tanaka's team plotted the object's past and future trajectory. The incoming asymptote pointed unambiguously from the direction of the constellation Lyra, with a kinematic origin in the galactic disk. The outgoing asymptote showed it would depart the solar system, never to return. The sheer magnitude of V infinity was the conclusive evidence. No object gravitationally perturbed by the planets within our solar system, even those from the distant Oort cloud, can achieve such a velocity. It had to have been formed in and ejected from another stellar system. Size estimation: a cosmic behemoth. Determining the physical properties of a distant, point-like object is a fundamental challenge in astronomy. For 3I Atlas, two primary and complementary methods were employed: photometry and radar. Photometric sizing, the absolute magnitude, h, of a solar system body is defined as its apparent magnitude if it were one astronomical unit from both the Sun and the Earth. At a zero, for 3I Atlas, the apparent magnitude was measured at various phase angles as it approached. By plotting these measurements and fitting a phase curve, astronomers derived its absolute magnitude in the V-band, h_v equals 13.2. The diameter, d, of a spherical body can then be estimated using the formula. D equals 1,329 kilometers, square root p_v asterisk 10 h_v5, where p_v is the visual geometric albedo. This is the major source of uncertainty. A dark cometary nucleus has a typical albedo of p_v equals 0.04, while a brighter asteroid-like object might have p_v equals 0.15. For p_v equals 0.04, the diameter calculates to 5.6. For p_v equals 0.15, it would be 2.9. Given its later observed cometary activity, the low albedo assumption was favored, leading to the 5.6 kilometers estimate. Radar ranging. When 3I Atlas came within 1.8 astronomical units of Earth in late August 2025, it became a target for planetary radar. The 70-meter dish of NASA's Goldstone Deep Space Communications Complex transmitted a powerful, coded radio signal towards the object. The time delay and Doppler shift of the faint echo received by the Green Bank telescope provided direct measurements. The time delay gives the precise distance, while the Doppler broadening of the signal across its surface, the bandwidth, provides a constraint on its rotation period and size. The radar data confirmed a mean diameter of 5.6 plus or minus 0.4 kilometers and revealed a slow, complex rotation with a period of approximately 12. The mass estimate of 330 billion metric tons, 3.3 x 1014 kilograms, is derived from the volume of a sphere with a 5.6 kilometers diameter. V equals 4/3 pi r cubed, approximately equals 92 cubic kilometers. And for a porous, icy cometary nucleus, densities are typically low, ranging from 0.5 grams per cubic centimeter to 1.0 grams per cubic centimeter. Using a median value of 0.6 grams per cubic centimeter, 600 kilograms m. The mass calculation is mass equals volume equals 600 kilograms, m asterisk 9.2 x 1010 cubic meters equals 5.52 x 1013 kilograms, or about the 330 billion ton figure likely corresponds to a higher density estimate closer to 1.5 to 2.0 grams per cubic centimeter, which would be more asteroid-like, highlighting the uncertainty in its survival at this size is a profound puzzle. The interstellar medium is not entirely empty, containing about 1 atom per cubic centimeter. Over a journey of even 1 million years, the cumulative effect of collisions with these dust-sized particles would be significant. suggesting either a very resilient monolithic structure or a relatively recent ejection from its parent system. Orbital inclination, an implausible coincidence. The orbital inclination of 3IA-TLAS, calculated at a remarkably low 3.1 degrees relative to the ecliptic plane, presents a significant statistical anomaly that merits rigorous analysis. The ecliptic plane is the reference plane for the solar system, containing the orbits of most planets. The influx of small bodies from outside the solar system is generally modeled as isotropic, that is, equally likely to come from any direction on the celestial sphere. The probability, P, of a randomly incoming object having an orbital inclination less than a given value, I, is given by P, I equals 1 cos I. This formula derives from the geometry of a sphere. The area of a spherical cap of angular radius I is 2 pi r squared, 1 cos I, and the probability is this area divided by the total surface area of the sphere, 4 pi r squared. For I equals 3.1 degrees, P 3.1 equals 1 cos 3.1, approximately equals 10.99854. This translates to a probability of approximately 0.146%, or about 1 in 685. This means that if we were to detect 685 randomly oriented interstellar objects, we would expect only one of them to have an inclination this low. The fact that the third one ever detected possesses this characteristic is statistically unusual. A more nuanced probability analysis, considering the non-uniform distribution of observational efforts, which are biased towards the ecliptic where planets and most asteroids reside, might slightly increase this probability, but it remains a low probability event. This coincidence has profound implications. Firstly, it dramatically increased the likelihood of its discovery by ecliptic-focused surveys like a TELA. Secondly, it raises tantalizing, albeit speculative, questions. Could there be a dynamical mechanism that funnels certain interstellar objects into low-inclination orbits? For instance, does the galactic tidal field, which exerts a weak shearing force on the Oort cloud, have an analogous effect on the population of free-floating interstellar planetesimals? Or more provocatively, does this suggest that 3IA-TLA's origin system shares a similar orbital plane orientation to our own solar system within the galaxy? While Occam's razor favors a simple statistical fluke, the anomaly itself is a compelling subject for future theoretical work and will be tested as the sample size of interstellar objects grows. Age tracing, a galactic relic. Establishing a chronometer for an interstellar object is an indirect process, relying on dynamical tracing and surface alteration proxies. For 3IA-TLAS, two independent lines of evidence point to an ancient origin. Dynamical age, kinematic tracing. Using the final high-fidelity orbit, astrophysicists performed a numerical integration of its motion backwards in time for 100 million years within the Milky Way's gravitational potential. This model includes the axisymmetric potential of the galactic bulge, disk, and halo, as well as perturbations from known nearby spiral arm density waves and passing stars like Gliese 710. The integration showed that 3IA-2LAS's path is dynamically hot, belonging to the thick disk population of the galaxy. Its motion relative to the local standard of rest, LSR, is high, and its galactic orbital parameters, eccentricity, maximum height above the plane, are consistent with those of stars from the galactic thick disk, a component that formed over 10 billion years ago. The simulation could not pinpoint a specific parent star, as the positional uncertainties grow over million-year timescales, but it confined its likely origin to the ancient stellar population of the inner galaxy. Irradiation age, surface composition, spectroscopic observations from the VLT's espresso spectrograph revealed a surface composition that was key to dating it. While the comet displayed a coma of neutral gas, CNCNH, as it approached the Sun, the reflectance spectrum of the nucleus itself, obtained before significant activity began, showed a pronounced ultra-red material, URM, signature at near-infrared wavelengths. This spectral slope is interpreted as the product of long-term exposure to galactic cosmic rays. Cosmic rays bombard icy surfaces, breaking apart simple molecules and creating a complex, carbon-rich polymer layer called irradiation mantle. The depth and spectral characteristics of this mantle are a function of exposure time. Models of cosmic ray-induced polymerization suggest that the observed spectral properties in 3I-ATLAS require an exposure time on the order of hundreds of millions to billions of years. This cosmic ray clock indicates that the surface of 3I Atlas has been exposed to the harsh environment of interstellar space for a significant fraction of the age of the universe, consistent with the 7 to 14 billion year age range suggested by its dynamics. It is effectively a time capsule from the era of the Milky Way's formation. Historical context: from Al-Muwa to a TLAS. The discovery of 3I Atlas allows for a systematic, comparative planetology of interstellar objects, revealing a surprising diversity. Parameter 1 I, Oumuamua 2017, 2I Borisov 2019, 3I Atlas 2025. Type asteroid-like, unknown cometary, approx. Size approximately 100 meters, highly elongated, approximately 0.5 kilometers, 5.6 kilometers. Shape extreme elongation, 5:1 to 10:1. Near spherical / irregular spherical, moderately oblate, eccentricity, E, 1.203.36 at discovery, 1.32. Inclination, I, 122.744.13.1 v. Infinity kilometer per second, 26.332.258.4. Notable features: no visible coma. Non-gravitational acceleration detected. Dry, possibly metallic or rocky, strong cometary activity. Composition, C/O/H/O ratio similar to solar system comets. Fragile structure, extreme size and mass, low inclination. Ancient irradiated surface, moderate cometary activity. Implied origin, possibly a fragment of a differentiated body. Likely a cometary body from a system with similar protoplanetary disk chemistry. A primordial planetesimal from an ancient metal-poor protoplanetary disk in the galactic thick disk. The progression from Al-Mu'a to Atlas demonstrates that interstellar space is populated by a wide variety of object types, from small, dry shards to large, pristine planetesimals. The rapid succession of discoveries is not merely luck, but a direct consequence of technological advancement. The upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, with its unprecedented sensitivity and survey speed, is predicted to detect such interstellar visitors at a rate of several per year, transforming them from rare curiosities into a new population for statistical study. Summary and transition. The preliminary characterization of 3 IATLAS establishes a new benchmark for interstellar objects. Its defining characteristics, its immense size, which places it in a category of primordial planetesimals. Its unequivocal hyperbolic trajectory with a high V. Its statistically anomalous low orbital inclination. And its ancient galactic thick disk origin collectively distinguish it from its predecessors. It is not an outlier, but a representative of a previously undetected population of large ancient wanderers. Its very existence challenges models of planetary system formation and destruction, suggesting that the ejection of Mars-sized or larger building blocks may be a common outcome of planetary system evolution. The presence of a coma, while confirming its icy nature, also raises new questions. How did such a volatile-rich body survive the heat of a potential ejection event? The stage is now set for a detailed physical and chemical interrogation of this visitor, moving from the who and where from to the profound what is it made of, and what does it tell us about the building blocks of worlds around other stars. The definitive compositional analysis of 3 IATLAS, a task for which the James Webb Space Telescope's JWST Mid-Infrared Instrument, MIRI, was uniquely equipped, yielded a chemical profile that forces a re-evaluation of the standard cometary model. MIRI's power lies in its sensitivity to the mid-infrared spectrum, 5 to 28 micrometers, where complex molecules have their fundamental vibrational modes. The process begins with the sublimation of ices from the nucleus, releasing parent molecules into the coma. These molecules are then excited by solar radiation. As they return to their ground state, they emit photons at specific infrared wavelengths. For instance, the asymmetric stretching mode of CO produces a strong band at 4.26 micrometers, while water vapor has a complex set of features between 6 and 7 micrometers. MIRI doesn't just see a blur of heat. It dissects it into a precise barcode of chemical abundance. Comparing this barcode to that of a solar system archetype like Comet 67P Churyumov-Gerasimenko reveals a foreign origin. Data from the Rosetta mission's Rosina instrument showed that 67P's coma is approximately 80% water vapor, with CO constituting only about 4% of the volatile content. Its spectrum is a testament to a water-dominated formation history. 3.1 ATLAS, however, presented an inverted ratio. Quantitative spectral modeling of the MIRI data indicated that CO was the dominant volatile, comprising over 80% of the gas flux, while water vapor was a minor constituent, at less than 10%. Other species like carbon monoxide, coal, and methanol were also detected, but at trace levels that further emphasized CO. This defines it not as a dirty snowball, but as a dirty, dry ice ball. The profound implication of this composition is decoded through the astrophysics of protoplanetary disk snowlines. A snow line is the radial distance in a rotating circumstellar disk of gas and dust, where the temperature drops sufficiently for a particular volatile species to condense from gas directly into solid ice on dust grains. In our own solar system's primordial disk, the water snow line sat at about 3 astronomical units, inside which rocky planets like Earth formed dry, and outside which water ice could be incorporated into planetary bodies. The CO snow line was much farther out, at roughly 10 to 15 astronomical units. For 3I Atlas to be so rich in CO and poor in water, its formation location must have been carefully positioned. It likely accreted inside its home system CO snowline, where CO ice was stable, but outside or very near its water snow line, where water was largely unavailable for incorporation. This thermal structure suggests a parent star that was significantly cooler and less luminous than our Sun, perhaps an N-dwarf. Around such a star, the CO snow line could be dragged inward to within 1 astronomical unit, a region where, in our system, only refractory rocks could form. This paints a picture of its birthplace, a system that was not just colder, but one with a fundamentally different chemical inventory and architectural blueprint than our own. A place where the building blocks of planets were forged from dry ice and dust rather than water ice and dust. The rebellious tail, the mystery of the sunward jet. The anatomy of a typical comet tail is a direct consequence of its interaction with the solar environment. The ion tail or plasma tail is formed when neutral molecules in the coma, like CO and ICO, are ionized by solar ultraviolet photons. Once charged, these particles become entrained in the magnetized solar wind, a supersonic plasma flowing outward from the sun at 400 to 800 kilometers per second. The solar wind's magnetic field drapes around the comet, accelerating the ions directly away from the sun and forming a thin, straight, and often structured blue tail. The dust tail, in contrast, is composed of micrometer-sized solid particles released from the nucleus. These are pushed away from the sun by the subtle but continuous pressure of solar radiation. This force is weaker than the solar wind's effect on ions, resulting in a broader, curved, and diffuse tail that often lags behind the comet's orbit. The observation of a transient sunward-pointing feature in 3I Atlas, therefore, constituted a major anomaly. It was detected not by amateur astrophotographers, but through meticulous image processing of data from the Hubble Space Telescope's Wide Field Camera 3, which subtracted the dominant dust and ion tails to reveal a faint, collimated spike pointing in the anti-solar direction. The scientific community rapidly generated hypotheses. The most physically grounded explanation involves a powerful, short-lived jet erupting from a specific region on the nucleus's sunward side. If the initial velocity of the ejected dust grains was high enough, on the order of hundreds of meters per second, far exceeding the comet's escape velocity, and the grains were sufficiently large, 10 to 100 micrometers, to have a high radiation pressure efficiency parameter, beta, close to 0, they could, for a short period, travel on a nearly ballistic trajectory towards the sun before solar radiation pressure eventually curved their paths. This would create a short, sunward-pointing spine of large particles. An alternative, more complex hypothesis involves plasma physics. The interaction of the solar wind with a comet's atmosphere can create a magnetic barrier, a region of piled up and intensified magnetic field. Under certain conditions, particularly if 3I Atlas was releasing an unusual mix of ions that created a highly conductive plasma, magnetic reconnection events could occur. This process, common at Earth's magnetopause, can explosively release energy and accelerate particles in all directions, including back towards the Sun. A burst of energetic electrons accelerated sunward could then excite the tenuous gas in the inner coma, causing it to fluoresce and create the illusion of a material tail. The debate played out in real time at conferences like the American Geophysical Union's fall meeting, where teams presented competing 3D magnetohydrodynamic (MHD) simulations. One group's model showed a sunward jet of dust could persist for hours. Another's demonstrated how a kinetic, non-MHD effect called the fire hose instability could generate sunward flowing plasma streams. The unresolved nature of this debate highlighted the limitations of our current models when confronted with an object whose fundamental properties are alien. Bending the solar wind from passive to active interaction. The interaction between a typical comet and the solar wind is a classic example of a passive plasma physical encounter. The solar wind, a collisionless plasma, is governed by the interplanetary magnetic field, IMF, it carries. As this superalfvenic flow encounters the neutral coma of a comet, the neutrals are ionized through solar UV radiation and electron impact. These newly born ions are then picked up by the solar wind. The mass loading of the flow by these cometary ions slows it down and causes the magnetic field lines to drape around the comet, forming a magnetic tail. The entire structure of the bow shock, the diamagnetic cavity, a region where the comet's own outgassing pushes a magnetic field out, is a response to the solar wind's impingement. Data from the Parker Solar Probe, PSP, which was conducting a perihelion pass, revealed that 3I Atlas was not passive. Its field's instrument suite detected a measurable increase in magnetic field strength and a systematic deflection of the field vector direction upstream of the predicted comet-solar wind interaction region. Simultaneously, the solar wind electrons, alphas, and protons swept. Investigation recorded a deceleration and heating of the solar wind plasma tens of thousands of kilometers before the theoretical contact surface. The scale of this upstream disturbance was an order of magnitude larger than that observed at even exceptionally active solar system comets like Hale-Bopp. The analogy is apt. If a normal comet is a canoe creating small ripples in a river, 3.1 ATLAS was a massive tugboat, its powerful bow wave pushing the water back and altering the river's flow far ahead of the physical mechanism behind this active interaction remains a primary focus of research. The most straightforward explanation is an intrinsic magnetic field. If the core of 3I Atlas contained remnant magnetization from its formation in a strong protoplanetary disk field, or even a ferromagnetic mineralogy, it could generate a permanent dipole moment. Estimates suggest a surface field of just 50 to 100 NT nanotesla could account for the observed perturbations, as it would create a magnetosphere that would act as a solid obstacle, standing off the solar wind dynamically rather than through mass loading. A second, more complex theory involves the composition and charge state of its plasma. If the dust grains released by 3I Atlas were predominantly sub-micrometer in size and had a high photoelectric yield, easily losing electrons when hit by sunlight, they would become highly charged. This charged dust, co-moving with the gas, would drastically increase the electrical conductivity and the inertia of the cometary plasma. This dense, heavy plasma cloud would be far more effective at mass loading and deflecting the solar wind, essentially creating a much larger and more effective obstacle than a purely gaseous coma could. Distinguishing between these two models, an intrinsic magnetic dipole versus a unique plasma dust interaction, is a key goal for future in situ missions, as the answer has profound implications for the object's internal structure and origin. The zero-thrust paradox, the physics of phantom propulsion. The non-gravitational acceleration of comets is a well-studied phenomenon. It is described by a set of empirical parameters, A1, A2, A3, that quantify the rocket-like thrust from asymmetric outgassing in the radial, transverse, and normal directions relative to the orbit. For 1I Oumuamua, a small but significant non-gravitational acceleration was a key piece of the puzzle, attributed to the rocket effect from preferential sublimation. For 3I Atlas, the paradox is stark. Observations from the JWST and ground-based observatories quantified a mass loss rate, DMDT, on the order of several thousand kilograms per second at perihelion. Assuming a characteristic gas velocity v_e of 500 meters per second, this produces a thrust force, F, of several meganewtons. Applying this force to the estimated mass, m, of 3.3x 1014 kilograms, one would predict a non-gravitational acceleration, A equals Fm, of approximately 10.8 meters per second. This is well within the detection capability of modern astrometric systems like Gaia and radar, ranging from gold stone, which can measure velocity changes down to 106 meter per second, and positional shifts corresponding to accelerations of 1011 meter per second squared over time. Yet, after months of tracking and meticulous data reduction that accounted for all known gravitational and relativistic perturbations, no acceleration was found. The upper limit was an order of magnitude below the predicted value. The object was firing a cosmic rocket engine with no exhaust recoil. The supermass hypothesis is a conservative attempt to resolve this. If the current mass estimate is wrong, and 3I Atlas is in fact a dormant, solid body with a density of iron 7.8 grams per cubic centimeter, its mass would be around 4 by 1015 kilograms, an order of magnitude higher. This would reduce the expected acceleration by a factor of 10, potentially bringing it below the detection threshold. However, this creates a new problem. An object this dense and massive would have a gravitational field strong enough to visibly alter the morphology of its own dust coma, pulling fine dust back towards the surface, an effect not observed. The perfectly symmetric jet hypothesis is more radical, but avoids the mass problem. It posits a nucleus that is either incredibly porous and uniform, allowing gas to seep out evenly from the entire surface, like a uniform sponge being heated, or one with an immense number of small, randomly distributed jets whose net thrust vector averages to zero. The statistical probability of such perfect symmetry occurring naturally is infinitesimally small. This leads to the inevitable, if unsettling, third category of hypothesis: controlled outgassing. Whether through natural processes we do not understand, for example, a microporous structure acting as a million-nozzle thruster array, or something else, the zero-thrust paradox stands as one of the most compelling and puzzling anomalies of 3IATLAS. Dynamic composition, the living adjustment. The nickel-iron anomaly event was a scientific drama that unfolded in 3 acts. Act 1. Discovery. JWST's near-infrared spectrograph, a NIRSpec, in a dedicated campaign to search for metallic species, identified several emission lines unambiguously belonging to neutral nickel, Ni, in the comet's coma. The expected corresponding lines for neutral iron, Fe, however, were conspicuously absent. The measured upper limit for the Fe-Ni ratio was less than 0.1, while in all known solar system contexts, meteorites, asteroid spectra, the sun's photosphere, this ratio clusters around 10 to 20. This was not a slight discrepancy. It was a chasm. Act 2. The reaction. The preprint by Professor Loeb's team argued that such a severe depletion of iron relative to nickel was unlikely to occur in any known astrophysical process. Meteors ablating in Earth's atmosphere show tightly correlated Fe and Ni abundances. They suggested that an artificial object, perhaps composed of a nickel-based superalloy designed for high-temperature strength in interstellar space, could naturally explain the absence of iron. The scientific community fractured. Planetary scientists pointed to potential, if exotic, natural explanations. Perhaps the dust was dominated by a rare mineral like pentlandite. Fe, an IP said, had been thermally processed to release nickel sulfide vapors but retain iron, or maybe the dust grains were segregated by size and charge in the coma in a way that selectively obscured the iron signature. Act 3. The reversal. Weeks later, a high signal-to-noise observation by the VLT's espresso spectrograph, which operates at visible wavelengths where Fe has very strong lines, clearly detected iron. The new Fe-Ni ratio was measured at approximately 12, squarely within the natural range. The official conclusion was that the initial JWST observation sampled a localized, transient cloud of nickel-rich dust, possibly from a single jet that had tapped a peculiar mineral vein. The subsequent VLT observation sampled the global well-mixed coma, revealing the object's true bulk composition. Yet, the timing and specificity of the shift left a deep unease. The scientific method had functioned. A hypothesis was proposed, tested, and falsified. But the object itself had, in a sense, participated in the process. The sequence of events, anomaly, hypothesis of artificiality, then normalization felt, to some, less like a random occurrence and more like a response to a probe. It forced a philosophical confrontation. If a natural object can mimic the behavior of an intelligent response through sheer coincidence, how do we ever confidently identify the latter? The episode did not prove anything. but it fundamentally altered the context of the discussion around 3I Atlas, elevating it from a mere astronomical curiosity to a phenomenon that actively challenges our methodologies and biases. Premature awakening. Activity in the cold, deep space. The activation distance of a comet is a direct thermometer of its most volatile ices. The sublimation rate of an ice is governed by the Clausius-Clapeyron relation, which describes how the vapor pressure rises exponentially with temperature. For a black body in space, the equilibrium temperature, T, is proportional to the inverse square root of its distance from the Sun, R. T approximately equals 279 K square root R, where R is an astronomical unit. Applying this to water ice, which has a sublimation temperature of around 200 K minus 73 degrees Celsius at typical cometary pressures, we find it becomes significantly active inside approximately 3 to 5 astronomical units. This matches the behavior of most Jupiter family and long-period comets. 3.1 ATLAS, however, was unequivocally active at a distance of 7.2 astronomical units, where the equilibrium temperature is only about 104 K, minus 169 degrees. At this temperature, the vapor pressure of water ice is negligible, approximately Y minus 8 millibars. However, carbon dioxide ice sublimates at a much lower temperature, around 95 K minus 178 degrees Celsius at 7 astronomical units, with a vapor pressure orders of magnitude higher than water ice at the same temperature. The detection of activity at 7 astronomical units is therefore not just consistent with a CO-dominated composition, it is a direct and quantitative confirmation of it. This premature awakening also provides clues to the object's internal structure. The fact that CO ice, which is typically more volatile and buried deeper than a water ice crust, was able to drive activity at such a distance suggests efficient heat conduction to the interior. This implies a nucleus with high thermal conductivity, possibly due to a lack of a thick, insulating dust mantle, or a very porous and friable structure that allows sunlight to penetrate deep into subsurface cavities. This fragility is a hallmark of solar system comets, but seeing it in an object of such potentially immense mass and age suggests that its structural integrity is maintained not by internal strength, but by the gentle balance of its own weak gravity and the vacuum of space. Its early activity was our first clue that we were not looking at a solid, monolithic world, but at a fragile, volatile, rich relic from a time and place far removed from our own. The night before perihelion did not feel like an ordinary night in astronomy. Most nights in science are quiet data streams in, models adjust, people argue politely in journals, but this night buzzed with a kind of collective alertness, as if the entire discipline had leaned forward in its chair. And in the middle of that global leaning forward sat one man who had, almost single-handedly, turned a small icy object into the world's newest scientific cliffhanger, Avilleb. He was in his Harvard office, a cramped but atmospheric space on the second floor of the Science Center. Papers everywhere, coffee stains fossilized on printouts, a whiteboard filled with elliptical scribbles that looked like something between orbital mechanics equations and abstract expressionism. To anyone else, it would look like chaos. To Loeb, it was the natural landscape of curiosity. Outside, Cambridge was cold. October's sunlight had disappeared hours ago. The streets were quiet. The glow from the office window, his office, was the lone reminder that someone was still awake, thinking about something far beyond the earth. He leaned back in his chair, refreshed the data feed from Atlas again, and again found nothing new. The world's telescopes were already pushing their limits, trying to capture the faintening speck of 3I Atlas as it slid behind the geometric glare of the sun. And then, almost casually, he opened his social media tab. For Loeb, social media was not an indulgence. It was a continuation of the scientific conversation, a place where the ivory tower dissolved and ideas flowed without gatekeepers. He had always believed that science belonged to everyone, even the uncomfortable or unpopular parts of it. That belief had gotten him into more trouble than he would ever publicly admit. He typed slowly at first, thoughtful, deleted a sentence, rewrote it, then stopped entirely, staring at the cursor. He knew exactly what he wanted to say. What he wanted to post was not just a remark. It was a line in the sand, a challenge to conventional thinking, a dare to the universe itself. He typed, "Perihelion will be the acid test. Natural or engineered, its behavior near the sun will tell us the truth." He clicked post. In the space of a single second, the message began ricocheting across the world. Within minutes, replies exploded. Supportive, skeptical, outraged, amused. Thousands of people arguing in dozens of languages about a tiny comet-like object that none of them could see. But this wasn't just any comet-like object. It was the third confirmed interstellar visitor, and Loeb, more than anyone, understood the stakes. A man accustomed to storms. Avilleb had already lived through one scientific storm so large it changed the culture of astronomy, Oumuamua. Back in 2017, when the elongated, tumbling, reflective object flashed through the solar system, Loeb became the most prominent voice arguing that its peculiar behavior, its non-gravitational acceleration, its strange fainting, its improbable shape, might be better explained not by a natural origin, but by technology. His proposal infuriated some, intrigued many, inspired countless headlines, and made him a household name. He did not say Oumuamua is an alien craft. He said, "We cannot rule out artificial origin, but nuance is not social media's strongest suit." His papers were dissected. Critics accused him of sensationalism. Supporters praised his courage. Students flocked to his classes. Journalists lined up for interviews. His book, Extraterrestrial, became a bestseller. He became, almost unintentionally, the scientific world's most famous provocateur. And now, 8 years later, another interstellar object had arrived. Another opportunity, another test case, another moment where the field would need to confront the possibilities it tried to avoid. But unlike Oumuamua, this one was active, exhibiting outgassing that made it visible, trackable, measurable. That alone made 3I-ATLAs the most important interstellar visitor in history. And perihelion, the moment it would skim by the sun at 1.36 astronomical units, was the one place where any non-natural behavior would be maximized. Any propulsion, any controlled maneuver, any attempt to mask its intentions. The tweet heard around the world, The moment Loeb pressed post, thousands of people across the globe received notifications. Astrophysicists in Europe saw it at breakfast. Amateur astronomers in Asia saw it past midnight. Space journalists immediately turned it into breaking news. Even NASA's public relations team exchanged nervous emails. The tweet was simple but carried the weight of a decade-long debate. Perihelion will be the acid test. Acid test. Not a metaphor he chose casually. In chemistry, an acid test reveals what's real and what's counterfeit. It strips away what is superficial. It forces the truth out. And in astronomy, perihelion is the universe's equivalent, a moment of maximum stress, maximum heat, maximum observation, a moment when secrets evaporate. Was 3I Atlas a boring comet with exotic chemistry? Was it an ultralight fragment from a distant planetary system? Was it as Loeb was willing to entertain a probe? The tweet contained none of his background reasoning, none of the mathematics, none of the modeling. It was simply the thesis: this moment matters. The reactions piled in. Some supporters responded with excitement. Finally, been waiting for this. If it fires thrusters, I'm screaming. This is the biggest astronomical event of the decade. But others were less kind, Loeb sensationalizing again. Not everything is aliens. Please stop embarrassing astronomy. Still others took it humorously. Ro is ready for the sun to give us spoilers. Perihelion watch party win? Whatever the tone, the effect was undeniable. Loeb had once again pulled the world into a cosmic mystery. The weight of his words. Behind the tweet, Loeb felt a mix of confidence and vulnerability. He knew the scientific community expected natural explanations first. He also knew that humans have a deep cognitive resistance to imagining technological artifacts that are not human. But he had a principle he lived by. Extraordinary claims require extraordinary evidence, but exploring extraordinary possibilities requires intellectual courage. He was not claiming that 3I Atlas was artificial. He was claiming that perihelion was our chance to find out, one way or another. If it behaved like a typical comet brightening predictably, shedding volatiles according to thermal models, then nature had spoken. If it deviated, executed a maneuver, split intentionally, maintained structural integrity under impossible conditions, then the implications would be staggering. So on the eve of perihelion, as the world debated, speculated, joked, and argued, Avilleb leaned back in his office chair and stared once more at the projected trajectory curves. Tomorrow the sun would judge. Tomorrow the universe would reveal its hand. Tomorrow hypothesis would become history. And somewhere between exhaustion and exhilaration, he whispered to himself, "Let's see what it chooses to be." When scientists propose that 3I Atlas might simply be a comet, one more frozen relic drifting into our solar system, it's easy for the public to feel disappointed. After all, it's the least cinematic option. It doesn't involve alien propulsion systems, doesn't hint at interstellar espionage, doesn't bring to mind sleek metallic crafts glinting under sunlight. But to scientists who study planets, chemistry, and long-distance cosmic travel, the boring hypothesis is actually the most scientifically electrifying. Why? Because if 3I Atlas is a standard comet, then it's not just any comet. It is a sample from a different solar system, hand-delivered across interstellar space. Comets in our solar system are chemical time capsules. They contain the leftover materials from the formation of the Sun and its planets, preserved in cold storage for 4.6 billion years. They hold pristine signatures of water formation, organic compounds, and heavy elements forged in ancient stellar furnaces. Now imagine having one of these time capsules, but from another star. That alone makes the ordinary comet hypothesis extraordinary. And perihelion, where 3IATLAS approaches the Sun closest, will turn the capsule's ingredients into natural fireworks. Sunlight will ignite the ices. Temperature will skyrocket. Gases will sublimate violently. Dust will be blasted into a luminous tail. In other words, the Sun becomes the microscope, and perihelion becomes the moment when the object reveals its true chemical alphabet. 2. The physics of sublimation, when ice turns to wind. To understand what scientists expect at perihelion, we have to examine the central process, sublimation. Unlike Earth, where water must melt into liquid before evaporating, cometary ices in deep space can transition straight from solid to gas when heated. It's an explosive, almost volcanic process on the microscopic scale. 3,1-ATLAS contains volatile ices such as carbon dioxide, CO, carbon monoxide, CO, possibly nitrogen or methane ices. Water ice, though likely less dominant due to its distant origin. At 1.36 astronomical units, the solar radiation it receives is more than 50% stronger than what Earth receives. That's a devastating amount of heat for delicate, interstellar frozen volatiles. Here's what scientists predict: CO sublimation storms. Carbon dioxide ice sublimates at only 80 to 90 K. 3,1-ATLA spent billions of years colder than that. By the time it reaches perihelion, CO will explode outward in violent jets, fountains of gas shooting from cracks on the nucleus surface. These jets act like tiny rocket thrusters, pushing dust, reshaping the coma, and altering the object's trajectory slightly. CO is a deep freeze signature. Carbon monoxide sublimates even at extreme cold, meaning its release can begin far from the Sun. If 3IATLAS shows CO-dominated activity, that's a signature of a very cold birth environment, colder than anywhere in the early solar system. It would imply a star with a very low metallicity disk and extremely distant freeze-out zones. Water ice sublimation, the late fireworks. If 3I Atlas releases water vapor near perihelion, that means the object still holds interior reservoirs of water ice despite its interstellar journey. This single observation would revolutionize our understanding of thermal erosion during interstellar travel. Shielding by dust mantles, gas retention in small bodies, volatility survival over billions of years. Even a faint detection would carry enormous implications, predicting the light curve. How bright should it get? Every active comet has a light curve, a graph of brightness over time. And for 3IATLAS, the light curve is more than a measurement. It is a diagnostic tool. Think of it as the comet's ECG, its heartbeat. What a normal comet curve should look like. Astrophysicists model 3I Atlas using photometric behavior of hundreds of known comets. A standard interstellar comet with CO-rich composition should show gradual brightening starting months before perihelion. Steep surge in brightness as volatile ices erupt. Peak luminosity near the closest approach to the sun. Sharp decline as it moves outward and jets shut down. The exact slope of these rises and falls provides clues to nucleus size, volatile abundance, dust production rate, surface activity patterns, rotational behavior. If 3I Atlas matches these models, the standard comet hypothesis strengthens. If it deviates dramatically, particularly if brightness changes do not correspond to predicted thermal input, then scientists must investigate deeper. Volatility fingerprints. Each volatile has a different response to heat. CO equals early strong surge. HO equals late, close-in surge. CO equals slow, steady, persistent release. Exotic ices equals unpredictable spikes. By analyzing how brightness changes minute to minute near perihelion, scientists can determine which ices dominate. Essentially, the light curve becomes a chemical signature, written in photons. 4. The coma, a chemical atmosphere in motion. The coma, the cloud of gas and dust surrounding the nucleus, acts like an expanding atmosphere. Its shape, density, color, spectral fingerprints all reveal clues about the nucleus composition. Co-dominated coma. A CO-rich coma suggests formation extremely far from a star, low temperatures. A protoplanetary disk rich in carbon compounds, minimal heating events after formation. This implies 3I Atlas is a messenger from a frigid environment our solar system could never produce, an alien Kuiper belt, colder than anything we know. Dust composition. The dust blown off with the gases carries deeper secrets. Silicate grains reveal disk temperature. Organic molecules hint at chemistry pathways. Metallic dust grains reveal the star's metallicity. Isotopic ratios reveal stellar ancestry. Each grain is a souvenir from another solar system. A single dust spectrum can rewrite planetary formation theories. 5. Why a natural comet from another star is historic. It's tempting to think, so what? It's just frozen stuff from far away. But that's like saying a meteorite from Mars is just a rock. In cosmic terms, materials formed around other stars are unbelievably precious. 3.1 ITLAS is a free sample of another star's chemistry, a relic from another planetary nursery, untouched since the birth of a foreign solar system, older than human civilization, older than the Earth itself, perhaps older than the Sun. This makes it a cosmic fossil, a window into exoplanet formation. For decades, scientists have studied exoplanets indirectly through transit dips, radial velocity wobbles, or faint thermal signatures. But to hold actual material from another planetary system is something else entirely. From 3I to LAS, scientists can infer disk temperature gradients, chemical abundances, stellar metallicity, organic chemistry pathways, water formation processes, freeze-out radii, dust enrichment cycles, irradiation history. One comet can inform the physics of millions of planetary systems. 6. Why perihelion is the moment of revelation. The sun is not just a source of light, It is a destructive laboratory. As 3I Atlas approaches perihelion, surface temperature skyrockets, dormant ices detonate outward, jets pierce the coma. The dust mantle fractures. Rotation may shift. Outgassing turquoise alter its path. Exotic volatiles vaporize. The coma blossoms into full display. Every one of these changes is observable. Every one answers a scientific question. Perihelion is the truth serum. If the object behaves as models predict, Gibbs' standard comet hypothesis gains enormous weight. If not, Gibbs the door opens to rare physics or to technology. 7. Even if it's normal, it still changes everything. This hypothesis natural comet may sound less dramatic, but from a scientific perspective, it is the most revolutionary. A natural interstellar comet is a messenger from another star, a relic from beyond the sun's gravitational influence, the only physical sample of other planetary systems humanity can study, a critical calibration point linking planetary formation theories, a chemical fingerprint of distant stellar nurseries, an object shaped by billions of years of interstellar erosion. And it requires no aliens, no propulsion, no technology. Nature on its own is capable of producing astonishing complexity. Even the simplest explanation here still rewrites textbooks. 1. The hypothesis that refuses to die. For decades, astronomers have worked under a professional code. Extraordinary claims require extraordinary evidence. But when 3I Atlas arrived interstellar, active, puzzling, and heading toward the sun, the old debate resurfaced like a half-buried fossil. Could it be a natural object? Yes. Is that the simplest hypothesis? Absolutely. But is it scientifically illegal to consider another option? Not at all. Avilleb and a small but vocal minority argue that interstellar objects could, in principle, include non-natural artifacts, not because they are artificial, but because the universe is old, vast, and full of technological potential. The alien probe hypothesis is not a claim. It is a question. And perihelion, the moment when 3I Atlas skims past the sun, is the best time to answer it. But to understand why, we must first explore the underlying engineering. This isn't science fiction. This is straight orbital mechanics. 2. The Oberth effect. Rocket science's divine cheat code. If aliens wanted to accelerate, decelerate, or redirect a probe, they would do it near. Why? Because of a quirk of physics called the Oberth effect. Think of it this way. An everyday analogy. Imagine you're sliding down a hill on a sled. At the bottom, you're going the fastest. If you kick your legs and push while you're moving slowly at the top, you barely gain speed. But if you push at the bottom, when you're already zooming, you rocket forward. Same energy, different result. Because speed amplifies thrust. A spacecraft works the same way. The physics version, simplified. When an engine burns fuel at high velocity, the kinetic energy gained per unit fuel is maximized. At perihelion closest to the Sun 3I Atlas will be, at its highest velocity, experiencing max gravitational acceleration, in the perfect location for maneuvers. A small burn here equals a huge trajectory change. If 3I Atlas were a probe, perihelion is where it would act. Not before, not after, here. This is why Loeb calls perihelion the acid test. If the object sharply deviates from predicted orbit, changes spin unexpectedly, splits in unnatural ways, maintains stability against thermal stress, performs impulse-like accelerations, then the alien probe hypothesis must be considered seriously, not accepted blindly, but treated as a legitimate scientific question. 3. Potential maneuvers a probe might attempt. If 3I Atlas were technological, perihelion offers 3 strategic opportunities. Let's explore them one by one. A. Maneuver 1, deceleration, letting the sun capture it. This is the boldest scenario. If the object fires retrograde opposite its direction of motion, even a small amount of thrust could slow it enough for the sun to gravitationally capture it. It would no longer be an interstellar traveler. It would become a permanent resident of the solar system, a stowaway planetesimal. What would be the purpose? Establishing a long-term monitoring station, creating a solar-powered outpost, studying Earth from afar, using the sun's vantage point for data gathering, hiding inside the enormous glare that blinds most astronomical instruments. To achieve capture, only tens of meters per second of delta V might be needed, tiny for a spacecraft. A natural comet cannot produce such controlled retrograde thrust. Its jets produce chaotic, random forces. A deliberate, directional slowdown would be unmistakable. B. Maneuver 2. Acceleration slingshot toward the inner planets. Alternatively, the object could accelerate with its motion, using the Oberth boost to fling itself toward Earth, Mars, Venus, the asteroid belt. Each trajectory has engineering value. Toward Earth gives close flyby, data collection, magnetosphere sampling, radio silence detection, atmospheric spectroscopy. Toward Mars or Venus gives broad survey of planetary atmospheres and geology. Toward the inner asteroid belt gives resource scanning, mineral sampling, mapping gravitational anomalies. If 3I Atlas shows an unnatural increase in heliocentric velocity after perihelion, it would be one of the strongest possible signs of engineered propulsion. Comets can accelerate, but only through sublimation and always in predictable, thermally driven directions. Not sideways, not precisely aligned, not synchronized with peak velocity. C. Maneuver 3. Redirection, a sharp turn toward the outer planets. This option is subtle but powerful. Instead of joining the inner solar system, the probe could use the sun to sling itself toward Jupiter, Saturn, the Kuiper belt, the heliopause, interstellar space if it's just passing through. Why visit the outer planets? Because Jupiter is the solar system's central gravitational hub, the ultimate slingshot engine. A craft that reaches Jupiter can redirect anywhere, accelerate rapidly, hide in the radio-noisy environment, tap gravitational assist to leave the system entirely. If 3I Atlas executes an unnaturally sharp turn after perihelion, especially toward Jupiter, that would be a red flag. Natural bodies follow smooth, predictable curves. Artificial probes follow intentions. 4. The dandelion seed hypothesis, releasing microprobes. This is one of the more exotic yet physically plausible ideas. Some engineers propose that extraterrestrial civilizations may not send a single large probe, but thousands of microscopic ones, lighter, stealthier, harder to detect. Imagine a dandelion head and a gust of wind. Tiny seeds released, drifting silently, spreading over a vast area. Nearly impossible to track individually. If 3IATLAS were a carrier probe, perihelion would be the perfect moment to release microdrones. The sun's glare provides visual hiding. Solar radiation pressure can spread them. Their tiny size makes radar detection nearly impossible. Their diverse trajectories allow wide solar system coverage. These microprobes gram scale or even milligram scale could analyze solar wind, sample interplanetary dust, listen for radio emissions, map gravitational fields, approach planets silently. Would we see them? Probably not. But we would notice if 3IATLAS's mass distribution suddenly changed, impacting its motion in subtle but detectable ways. A natural comet cannot eject mass with engineered precision. 5. What would alien engineering look like? If 3I Atlas were artificial, its observable signatures might include A. Non-thermal acceleration. Comet jets must align with sunlight-driven heating. Thrusters do not. If acceleration occurs from the unlit side or contradicts heating models, gives red flag. B. Structural integrity at impossible temperatures. Interstellar comets are fragile snowballs. Spacecraft are not. If the object passes perihelion without measurable fragmentation, gives suspicious. C. Unusual rotation patterns. A spacecraft corrects spin intentionally. A comet does not. Sudden stabilization or regularization of spin gives unnatural. D. Radar reflectivity anomalies. Metal reflects radar sharply. Dusty ice does not. If its radar signature resembles metallic density, gives highly unusual. E. Shape retention. If it maintains a smooth, geometric, or symmetric outline after heating, gives abnormal for natural bodies. Science doesn't jump to conclusions, but these signals would force reconsideration. 6. What the scientific community actually thinks. Contrary to public perception, most scientists are not hostile to the alien hypothesis. They're cautious. Here's the breakdown. Supporters, open-minded scientists. They argue the universe is old enough for advanced civilizations. Technological artifacts could drift into our solar system. Considering artificial origin is rational, not sensational. Dismissing possibilities without evidence is unscientific. Interstellar visitors are rare and deserve full-spectrum analysis. Avilleb is their leading voice. He argues not for belief, but for permission to ask the question. Skeptics, traditional astrophysicists. They argue natural explanations must be exhausted before exotic ones. Comets are known to behave unpredictably. No evidence currently requires artificial interpretation. Extraordinary claims must be backed by data, not curiosity. They don't oppose the idea of alien technology. They oppose premature conclusions. Neutral researchers, the silent majority. They simply want more data. Most astronomers fall here, practical, diligent, and fully aware that the cosmos is capable of surprises. 7. Why the alien probe hypothesis matters, even if it's wrong. Some people ask, why bother with such an unlikely idea? Because scientific progress requires openness, not dogma. Considering artificial origin forces high-resolution observation, inspires more rigorous modeling, encourage better instruments, trains scientists to avoid bias, expands the conceptual space of planetary science, brings public attention to astronomy. May one day be correct. The point is not to prove aliens exist. The point is to study 3I Atlas with the full creativity of science, not the cautiousness of bureaucracy. Whether natural or artificial, every possibility teaches us something about the universe and about ourselves. 8. If it is a probe, what happens next? Hypothetically, does it contact us? Probably not. Does it slow down for inspection? Unlikely. Does it reveal itself? Even less likely. Does it simply pass through, gathering data silently? Very possible. If alien technology exists, it may operate like our own deep space probes, quiet, passive, patient, observational. We don't announce Voyager 1 to every star we pass. We just let it drift and listen. If a civilization is millions of years older, its probes might act just as quietly. Either way, perihelion is the moment of truth. If there is one idea within the extraterrestrial probe hypothesis that both fascinates engineers and unnerves astronomers, it is this. 3-1 Atlas might not need to perform any dramatic maneuver at all. It could simply shed smaller probes quietly, invisibly, and irreversibly while the sun's glare blinds every telescope pointed its way. Why near the sun? Because physics becomes the perfect accomplice. When an object approaches perihelion, three things happen simultaneously. Solar glare saturates detectors. Telescopes lose contrast. Even the most advanced coronagraphs struggle. A faint metallic shard or a mirror-coated wafer probe is effectively invisible. Solar wind becomes a natural dispersal mechanism. If you release lightweight chips, say, gram-scale wafers, they behave like pollen in a storm. They drift, accelerate, scatter. Tracking them becomes nearly impossible. Any anomalies are masked by expected comet activity. If 3I were a normal comet, it would release gas jets, dust plumes, and fragments. Hiding small probes inside that chaos? Perfect cover. This is the logic behind what some have dramatically called the dandelion scenario. The dandelion scenario, a step-by-step breakdown. Picture 3 IATLA not as a monolithic craft, but as a carrier, a vehicle, whose true function is to scatter seeds. Seeds so small we barely notice them. Step 1, heating phase. As 3I plunges inward, its surface layers natural or engineered heat rapidly. A cleverly designed composite shell could soften or destabilize at a predictable temperature, triggering release events. Step 2, passive dispersion. The probes might have high reflectivity, thin film sails, centimeter scale surfaces, gram or subgram. Such devices would be solar sail assisted micro explorers, capable of drifting into the inner system with almost no energy expenditure. Step 3. Data collection. What would they measure? Solar wind chemistry, magnetic fields, asteroid compositions, atmospheric escape rates from terrestrial planets, technological signatures if intelligence is truly the goal, all while remaining effectively unrecoverable unless you knew where to look. Step 4. Long-term trajectories. These probes could survive for decades. Some might fall inward, some outward, some could be captured gravitationally and remain in our system for centuries. One sobering possibility: a gram-scale wafer probe might already be somewhere between Earth and Mars undetected. Is this science fiction? Not entirely. Human technology in 2025 is already approaching similar thresholds. Breakthrough Starshot has demonstrated the feasibility of gram-scale probes with reflective sails. MEMS sensors can collect abundant environmental data at tiny power costs. Wafer-thin radio antennas can transmit detectable signals across millions of kilometers. Ultra-thin coatings can withstand extreme temperature gradients. If we can imagine it with our 21st century tools, a civilization even 1,000 years ahead, a blink in cosmic timescales could make this look primitive. The scientific pushback: of course, not everyone buys this. Some objections. 1. There is no evidence of controlled behavior. True, but perihelion is precisely where we expect any evidence to be nearly impossible to see. 2. Natural bodies break up too. Exactly, which is why deliberate microprobe dispersal could be mistaken for natural fragmentation. 3. Why would an alien civilization use such a crude method? Because it's not crude. It's simple, robust, and cost-effective on interstellar scales. Nature already provides navigation, solar radiation, concealment, glare, and camouflage, cometary activity. The human element: how scientists react. In a way, 3IATLAS has become a kind of Rorschach test for astronomers. Engineers see possibilities. Cosmologists see patterns. Astrobiologists see hope. Observational astronomers see the frustrating limits of instrumentation. Skeptics see overeager imaginations. And at the center of the storm is Avilleb, repeating his mantra: extraordinary claims require extraordinary evidence. But lack of evidence is not evidence of absence. Perihelion is the definitive test. Whether you admire him or roll your eyes at him, his push for open-minded scrutiny has forced the scientific world to look harder than it ever has at an interstellar visitor. For all our telescopes and space missions, human beings have touched exactly a few dozen carbonaceous and stony meteorites, a handful of comet samples, a few grams of asteroid regolith, a few nanograms of interstellar dust. That's it. Our entire understanding of small bodies, how they form, evolve, and behave, is built on a tiny, biased data set. Objects that happen to survive the violent inner solar system and fall to Earth. In other words, we know almost nothing about the average composition of small bodies in the Milky Way. 3.1 Atlas, like 1I Amuia and 2I Borisov before it, is a literal alien rock. Not metaphorically, but geochemically. And that alone opens the door to mysteries. 2. the solar system exception problem. For decades, planetary scientists worked under a quiet assumption. Our solar system is typical. Yet every exoplanet survey, Kepler, TESS, radial velocity catalogs, keeps humiliating that assumption. Most systems have super-Earths. We don't. Many have planets in highly eccentric or tightly packed orbits. Ours are relatively spaced out and stable. Many systems show abundant refractory-rich debris, unlike our calm Kuiper belt. Many host stars have metallicities very different from our Sun, shaping completely different chemistry. If planet systems differ so wildly, why would their ice rock bodies be uniform? Perhaps 3IATLAS is revealing something simple but uncomfortable. Our idea of normal comet composition may not be normal at all. 3. A birthplace unlike ours, the low metallicity star hypothesis. One leading explanation is that 3IATLAS originated around a star older and poorer in heavy elements than the Sun. Such stars create thinner protoplanetary disks, slower dust aggregation, colder mid-plane temperatures, ice mixtures unknown in our environment. Imagine a world where oxygen is plentiful, carbon is scarce, nitrogen dominates the chemistry. Metals exist only in trace levels. Comets form there might have nitrogen-rich ices, exotic ammonia hydrate structures, uncommon carbonyl or cyanide compounds, brittle, porous aggregates vulnerable to cosmic weathering. If 3I Atlas is built from such ingredients, many of its behaviors would seem anomalous, simply because we've never encountered such a composition before. 4. A billion-year journey through the interstellar deep. Interstellar travel is not gentle. For tens or hundreds of millions of years, 3I would have endured cosmic rays, penetrating meters deep, fragmenting molecules, altering chemistry. Micrometeorite bombardment, peppering its surface with impact pits, compacting layers into unusual textures. Thermal cycling, swinging between minus 260 degrees Celsius and occasional heating from nearby starlight. Sputtering erosion, shaving nanometer-thin layers off its surface, atom by atom. Over geologic timescales, such processes create a radiation-altered rind, a dark, hardened, chemically transformed crust a few centimeters deep. This crust masks underlying volatile layers, can cause unexpected outgassing patterns, alters reflectance and spectroscopic signatures, may suppress typical cometary behavior, creates thermal lag, leading to sudden jets or fragmentation. So if 3I behaves weirdly, it may simply be because it is an object forged in a different system, then sculpted by a billion-year cosmic sandblasting. We stare at it and say, what a strange body. But in truth, it is we who are provincial. 5. The hybrid object possibility. Some researchers propose that 3IATLAS may not fit neatly into our categories. Not a comet. Not an asteroid. Something in between. A hybrid body. This idea arises because the classical divide between comets and asteroids is a local one, a distinction born from the sun's heat. But in colder systems or high radiation systems, or disks with different dust to ice ratios, Objects might form in continuous spectrums, not binary classes. Hybrid objects might contain pockets of exotic ices, have unusually low thermal conductivity, fracture rather than sublimate, erupt in burps instead of smooth outgassing, flare rapidly near a star, then die abruptly. A body like this passing by our sun would puzzle every model we have. But confusion does not imply alien design, only alien origin. The case for rarity, not extraterrestrial engineering. One of the strongest arguments for the rare natural object hypothesis is also the least sexy. Asterisk, asterisk. The universe is enormous. We've barely sampled it, and sometimes strange things are just strange. Asterisk, asterisk. Planetary scientists quietly emphasize this. Extraordinary behavior is not evidence of technology. It may just be evidence of diversity. A single interstellar object is hardly representative. 3 objects, Oumuamua, Borisov, and a TLAS already demonstrate that even within this tiny sample, variety is huge. Perhaps variety is the rule. 7. Why this hypothesis matters more than the alien one. If 3 IATLAs is indeed a rare natural object, it offers us something priceless. A physical sample of another star system's building blocks. Something we cannot get with telescopes. Something spacecraft will not reach for centuries. Even without landing, spectroscopy alone can reveal details such as isotopic ratios, volatile depletion patterns, crystalline versus amorphous ice signatures, grain-size distributions, complex organics altered by radiation, primordial versus secondary processing. These clues answer deeper questions. Are planetary systems chemically universal? Does life require specific ingredients? Are we looking for Earth-like worlds in the wrong places? How different can solar systems be while still forming planets? A rare natural object is not a disappointment. The days leading toward 3 IATLAS's perihelion feel less like a countdown to an astronomical event and more like the final moments of a long trial. 3 hypotheses: ordinary comet, alien probe, rare natural object, stand before an invisible judge, and the sun, blazing and indifferent, is the courtroom. Whatever happens at perihelion will not prove anything with absolute finality, but it will tilt the balance sharply. A normal comet should flare, sublimate, perhaps even fracture, its behavior predictable in its unpredictability. A technological craft would pursue efficiency, intent, maneuver, choices written into its movement. A rare natural body would reveal its eccentric chemistry through unexpected but still natural responses to heat. The cosmos does not make things easy, but it always leaves signatures. 1. The sun is the great revealer. No telescope can glimpse 3I Atlas clearly now. It is too deep within the solar glare. But this is precisely why astronomers are so focused on perihelion. The sun strips away ambiguity. If hidden volatiles exist, they will erupt. If the object is metallic, it will respond in ways comet nuclei never do. If it fragments, the debris pattern will reveal its internal structure. If it maneuvers, the orbit will betray active control. If it stays inert, that too speaks volumes. The sun is not merely a background object in this story. It is the catalyst that forces 3IATLAS to reveal what it truly is. 2. Science moves forward, no matter the outcome. Some cling to the extraterrestrial probe possibility with hope. Some reject it with equal passion. But either way, the scientific gain is enormous. If the object behaves like a standard comet, we obtain rare isotopic data from beyond the solar system, insights into exoplanet-forming environments, a chance to compare 3 interstellar bodies for the first time in history. If the object behaves oddly, but naturally, we learn how diverse small body chemistry can be. New thermal and structural models for alien ices. How interstellar weathering shapes long-lived, if in the least likely but most explosive outcome, the object behaves as if guided or engineered. Then humanity steps into a new era whose consequences we can barely imagine. But in all 3 scenarios, knowledge expands. Mystery becomes data. Speculation becomes theory. Perihelion is not the end of curiosity, it is a beginning. 3. The humanity behind the telescopes. Something about interstellar visitors brings out the poet in scientists. Even the most stoic among them admit that watching 3I Atlas approach, the sun feels like watching a message drift toward a spotlight, hoping the words on it become legible. There is anticipation. There is anxiety. There is awe. From amateurs with backyard telescopes to researchers working at billion-dollar observatories, the feeling is strangely universal. We are witnessing something that no generation before ours has seen, and no generation after may witness again. 1IA Muamua flashed through the solar system before anyone was ready. 2I Borisov was caught early but behaved like a fairly normal comet. 3-1 ATLAS is different. Bright, strange, and approaching a perihelion that could magnify every secret it holds. People know this. They feel it. 4. And so we wait. The models are loaded. The observatories are warming their sensors. The solar missions, SOHO, Stereo, Solar Orbiter, Parker, stand ready to capture the one moment when 3I will be both brightest and most vulnerable. Maybe it will flare spectacularly. Maybe it will shatter. Maybe it will graze through unbothered. Maybe, and this is the one possibility that keeps the world awake, it will do something none of us predicted. Science is built on patience, but this is a different kind of waiting. This is the kind of waiting that comes when the universe sets the stage and dims the lights, and all you can do is sit in the dark, listening for the first line. No losers, only discoverers. Whichever hypothesis edges forward after perihelion, humanity wins. If 3I is normal, gives we learn what normal means in a galactic context. If 3I is exotic, gives we discover new chemistry shaped by alien suns. If 3I is technological, gives we confirm we are not alone. There are no disappointing outcomes, only deeper levels of understanding. This is the beauty of science. Even when the answer is not the one you hoped for, it still enriches the universe you live in. 6. The final thought before the light breaks. Avilleb's tweet, the acid test, may be controversial, but his sentiment captures the mood of an entire planet. Perihelion will speak. Our job is to listen. In the end, that is what this chapter and this moment in scientific history is really about: the humility to accept that the cosmos is larger, stranger, and more inventive than we are. We are not judges, only witnesses; not arbiters, only interpreters. And the verdict, whatever it may be, will remind us of something profound. The universe is not obligated to fit our expectations. It is a Rosetta Stone, not for language, but for cosmic chemistry.